I'd like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, CSIAC. Today's presentation is entitled Cybersecurity Game, a model-based game theoretic approach for mitigating cybersecurity risk. My name is Steve Warzala. I'm the CSIAC Outreach Manager. A few administrative notes before we begin. First, all phones have been muted except for the presenters. Questions may be asked anytime during the presentation by utilizing the chat function. Time permitting, your questions will be answered at the end of the session. Today's briefing slides will be posted on our website within a couple of days. And finally, I'd like to take a moment to acknowledge and thank our sponsor, the Defense Technical Information Center, DTIC. The funding that DTIC provides enables CSIAC to conduct these webinars. It's my pleasure to introduce our presenter for today's webinar, Mr. Scott Mussman. Scott is a principal engineer at the MITRE Corporation. He has been working on information security related problems since the mid-1990s. Most recently, he has been focusing on mission assurance by estimating and mitigating cyber-related mission risks. In addition to information security, Scott has conducted work in several other domain areas, including image understanding, decision support, data mining, as well as data planning and reasoning under uncertainty. Previously, Scott served as the Director of R&D for Integrated Management Services, Inc., and he was also the head of the Enterprise Security Research Group for AlphaTech BAE Systems. Scott holds degrees in engineering and computer science, respectively, from the University of Sussex and Johns Hopkins University. Good afternoon, Scott. The floor is now yours.
Hey, can everybody hear me?
Yes, we can.
Okay. Appreciate the opportunity to give the presentation. I wanted to, take the opportunity to introduce people to some work that we've been doing. It's work that's taken place over a number of years, and this is really sort of starting to be the culmination of what we were trying to achieve. Although, of course, everything is always, with research, is always a work in progress. There's things we can do, and I'll sort of summarize with some future work that's going on as well. Often like to take people that people know and respect, and utilize some of the facts that they share their words of wisdom with us. Carl Landwehr is one of those people. We used to work with him way back when. I think you mentioned I started off doing things like radar at the Naval Research Lab, which is where Carl came from originally. And this got the quote, which is basically the whole economic boom in cybersecurity is largely a consequence of poor engineering. And I think that often is, that actually is a quote that holds pretty well. So why do we want to improve our ability to do cybersecurity engineering? And what I'm proposing here is a form of what I call model-based engineering. And our goal is to improve the security of a system, but that requires spending money. And how do you justify that you're spending the money you ask people to give you to spend on it, and how do you maximize your return on investment for those for those expenditures? I would claim that a lot of the methods that people are applying today, including things like RMF, are pretty light on the providing the decision makers exactly the information that they need to make well-informed cybersecurity decisions. So this is an attempt to sort of present things in a more quantitative way. And your ultimate goal should be to help your organization succeed, as opposed to just make cyber stuff better. So this is not focused. This is focused on the holistic sort of this is what your organization is trying to accomplish. These are your missions. How do you make sure the cyberspace supports that in a resilient and secure manner? So what we're proposing and what we've implemented here is a method that is trying to use models of your system. So we focus people on being able to produce models that describe aspects of the system. Those are gathered, that information is gathered into these computable artifacts, which I'm going to read as the word model. And we apply game theory to them. The idea is you're using algorithms to do stuff that current risk assessors are doing in their head, and that is hopefully a game leveler so that you can ensure that things are done consistently and coherently and comprehensively every time. And then when you're done, the nice thing is you've got these computable models which basically represent all of the assumptions that went into your initial assessment. So that's essentially the approach that I'm going to be trying to describe. So truth in advertising, I can say, you know, I go to meetings and say, my name is Scott, and I have to admit that I view cybersecurity and resilience decision making as just another form of risk management. Basically, the goal, you know, basically the assumption is that pretty much everything you do to make your system more secure or more resilient is reducing some risks that are out there. I think it was about 5 or so years ago, MITRE was supporting DARPA in a program called the Mission Resilient Clouds. And one of the things we had to do was come up with a way to how do we measure the various performer technologies that were being developed for that. And that was sort of the genesis of what is now going to be coming out as a book chapter of the references at the bottom of this slide, which is basically saying you're using mission risk as a resilience metric. And so everything you do to increase resilience results in a reduction in your mission risk. And you're not trying to just make the cyber stuff better. You're trying to make the mission outcomes better. And you have to keep in mind that, you know, there's this notion about mission risk. It's a poorly defined term. But when you're trying to deal with cyber resilience and cybersecurity, it's more than just achieving your functional goals. So one of the examples of the system that we did some work on, did some analysis of using this method I'm describing today, was using mobile devices in e-medicine. And so one of the use cases for that was doctors using their mobile devices to do things like make patient referrals or to write prescriptions. And so, you know, functionally what that IT is there to support is those, you know, operational tasks for the doctors. But in the same time, you got to make sure that people can't use that IT in any way to do things like change a patient's medical record. Because if you change a patient's medical record, the doctor may think that's the real patient history and prescribe the wrong medicine, and they can kill the patient. So you're basically, you know, part of security is doing what you're trying to do in a functional way. I just lost it. People still seeing the slides?
Yes.
Okay, I'm sorry about that. Where was I? Yeah. So you basically have to do, you know, satisfy your security constraints as much as you can. The idea is you want to be able to focus on targeted improvements that are quantitative and up to whatever resource limits you have, because, you know, we could spend a lot of money. The question is, how much do we need to spend to make a real difference? And the cybersecurity game is essentially the realization of the metric that's described in this book chapter that's coming out. So one of the things that's described in the book chapter is what's called a security or resilience context. And this is something that I don't think people do enough of. You really have to formally document, this is what I'm trying to secure, this is the whole context of what you need to know about what I'm trying to secure, so that if somebody comes along and looks at it later, they know exactly, and they can work. You want to have two people make different assessments. You can do as much as you can to apples-to-apples comparisons. And so this context involves making sure that you're clear about the boundaries of the system. So if you are trying to, you know, make a power plant resilient from a cyber perspective, that's a little bit different than if you're trying to make the whole delivery of power all the way to the end user, because now you have the power plant and you have the transmission lines, and it changes the scope of the assessment, it changes what you do. You need to make sure you're clear about what your system boundaries are. You need to be clear about what incidents you're trying to protect against. It's very easy for a lot of people will focus on mission resilience and cyber resilience from a availability perspective, but you could be very, very resilient in terms of availability, but you can have no resilience in terms of anything with lots of confidentiality or integrity problems. So you pick which clear what you're focusing on. You have to be really clear what you're trying to measure, because the metrics, are you trying to save money? Are you trying to save lives? Make that clear. You have to make clear that, you're going to be doing this and looking over some time period, which is the next bullet. And you have to decide, am I caring about my worst case, my average case, my mean, a median case? There's all sorts of ways you can look at those metrics, and you just have to be clear what it is you're really trying to optimize your decision about. And then then the other part is you have to characterize whatever uncertainties you have, because very rarely are things cut and dry in cybersecurity. So I'll sort of try and introduce why the game theory matters. Back in 2008, the National Research Council did a study. They were really focusing on terrorism as opposed to cybersecurity. And what they concluded was that traditional risk analysis with the things like event trees and fault trees is just not suited for problems where you're dealing with an intelligent adversary. And so the example that's shown on the slide essentially is traditional event tree on the left, where there's things that can happen and probabilities that you can go either way on each path, versus what you see on the right, which is a game tree, which is basically saying, well, once the attacker's move, he's going to do the worst thing he can do, but if the defender's move, he's going to try and minimize the worst thing that can happen. And sure enough, if you just run down the math of these things, the game tree is going to make us a different recommendation of what the optimal answer is. And that matters, especially as you scale up to real problems with lots of different assets and effects that get taken into account. And essentially what you're doing here is taking into account that, the traditional fault risk analysis approach is kind of like if your defender and your attacker both get to make their decisions at the same time, and then you just let things go. But that's not what happens. I mean, part of the cyber kill chain is reconnaissance. So the first thing that an attacker is going to do is do reconnaissance and then adjust everything that they're going to do based on what they've seen that you protected and what they think you've not protected. And so Tony Cox is the editor-in-chief of the Risk Analysis Journal. He wrote a paper back in 2009 on game theory and risk analysis. He includes this quote about non-game theoretic approaches can make recommendations and predictions that are pretty much irrelevant for effective risk assessment and management in these adversarial situations. And the basic assumption is that defender strategies that fail to consider how the attacker is going to observe what they can observe, and then adapt what they're doing based on what they can observe about what the defender has defended, just don't work. So give a very, very simple example. Here's a very, very simple system. There's an attacker out there on the outside. There is one server here. It has some treasure on it. We say its value is 100K. If you do nothing, the attacker can essentially attack that server. And there's some probability. In this case, it's the attacker model would be maybe 1 in 1,000 attempts will succeed. And you get an expected value of, like if this is the probability the attacker is going to attack this particular server, and this is what the impact is if he does that. If you make it impossible for the attackers from the outside to connect to that server, well, there's other things on the network that do interact with the outside, so they become the targets. And so you essentially make, given the attacker, well, what's his next best route? In this case, there's no defenses that are there, and so there's an expected value which is much lower than the original expected value, but it's still a viable attack path. If you defend that particular attack path, well, keep in mind that there's all these other clients that are out there, and they can be used as stepping stones for attacking the server. And so you really have to, you really haven't accomplished very much in this case until you've protected against all of those clients. And that's pretty much sort of the intuition about why everybody runs antivirus and security tools on our laptops and workstations, even though we may not have anything valuable just on them by themselves. So without a defensive action, there's sort of an obvious path to the defender. As the defender starts to do things, the attacker will start to look at the alternate pathways. And the total risk here would be a simple way to do this is you sum up all those expected values or you could be take the worst case if you want to be pessimistic. And to be able to play this as a game, you need a way to compute impacts, you need to be able to compute attacker pathways, and you need to be able to represent all your defense methods, which finally gets us into sort of an overview of the security game. This is all the rest of this talk is about. I will go into details about the different elements there, but essentially this is sort of the, if you get this part, then everything else is just more details. But essentially we're focusing on being able to characterize a mission and the system that supports that mission by building some models. You build a mission impact model, you build a cyber terrain model, we provide an attacker model that you can modify if you want to, and we provide some defender models that you can augment again if you prefer, don't like what we can give you. You use the results of those models to compute attack trees, and again I'll go into this in more details, which are essentially computing the likelihood that compromises will happen. And then you start doing the game analysis where you say for every defensive move you make, you combine that with what the attacker would do if you did that, and you get the game trees, and you start composing these things together, and you get essentially a portfolio analysis, which I will go through in more detail. But that's essentially the process I'm describing. The models that we talk about, I'll go into details more about the CMIA process model, which essentially is mission impact. CMIA stands for Cyber Mission Impact Assessment, and you have to essentially go figure out what your consequences are. Then we have a model of the cyber terrain. I call this the cyber terrain model because it's basically sort of the cyber topology overlaid with things like access and trust relationships, which are not necessarily just obvious in a network diagram. So this is a computable version of what the cyber terrain looks like. We provide an attacker move model, which shows how an attacker can move over the terrain that you defined, and we provide some models that describe what you can do as a defender. And again, I'll go into more detail with these in more detail. I think this is largely unique in terms of the fact that, and I lost track of the screen. Let's come back to me again. Apologize about that. I don't know if it's just on my end. But the idea really is these models are now all interconnected with a bunch of algorithms. So if I do something like add a redundant path in this process, it will have a result. It can change the result of the risk assessment. If I change the types of some of these assets that are here, so I can do diversity or those kind of things, or if I change the access controls, those will all mathematically map to changes in the risk estimate. So, and I think this is one of the few systems that actually allows you to do all that stuff by just changing aspects of the model. So, start off by figuring out what your consequence space is, form what's called a cyber mission impact assessment model, and we do that using, our focus is on process modeling. And again, I'm losing the screen, so. Somewhat difficult. Okay, it's back. Yeah, I apologize for this. I keep losing the screen on my end, and then so it's hard to keep track of what I was just about to say. But essentially, we're using process models to represent the mission process and map that to cyber impacts. It's meant to be focusing on the losses that occur. It's meant to be quantitative, and it's meant to guide your mitigation analysis by focusing on what are the critical assets and what are the types of protections that those critical assets are going to need. And I'll get into that in the next examples. Yeah, okay, here we go. So one of the questions that always comes up is, how do you comprehensively reason about all the possible cyber attacks that can happen? If you look at something like CVE, this is out of date already. There's over 80,000 entries in CVE. If you look at things like the CAPAC, the Common Pattern Enumeration, there's over 500 patterns in there. That's just an awful lot. And this is some nice graphics that a colleague of mine, Dr. Steve Knoll, put together, which sort of show this is injection, and then the other element below it is just a blow up of all the different injection attacks. So you need to know an awful lot about cybersecurity, and you need to know a lot about all these spaces if you're going to be trying to be dealing with attack instances. So we don't recommend that. What we recommend is that people focus on what we call incident effects. And most people have no trouble at all thinking about confidentiality, integrity, and availability. We found that we wanted to go a little bit further with that, so we came up with a acronym we call DIMFUI. It's hopefully became a word that will add it to the dictionary at some point. But essentially, we focus on degradation, interruption, modification, fabrication, unauthorized use, and interception. And these are essentially meant to be states of cyber assets. So we don't care how the attacker can change those state values. That we just care that if the attacker is able to change, is able to interrupt. If somebody is able to modify some cyber asset, will it have an impact on my mission outcome? And this is and our claim, which is stuff that people have yet to refute, is that any of the cyber attacks you see in things like HAPEC or CVE in particular are just manifestations of one or more of these effects being applied to one or more cyber assets using some particular method. And here we sort of abstracted out the way in the method. Again, there's a paper that describes this in more detail. The method we recommend is to try and build the impact models focusing on unacceptable and desired outcomes. If any of you are familiar with the book that Nancy Levinson wrote called Engineering a Safer World, her chapter 10 has this concept of defining your safety goal. And we're essentially trying to copy that, except for keep in mind that, she's focusing on engineering safety, which is primarily about natural hazards, and we're focusing more on cyberspace, where attacker, if the attacker can do it, they'll probably want to do that. And so this will always be a set of mission and system specific type of things. The outcomes will always be, we're trying to quantitatively assign outcomes to the various the bad things that you want to occur. And what you're trying to do by adding security or resilience methods to your system is to prevent these things from either occurring or to reduce the chances of the impacts that happen when they do occur. And so essentially what you're going to be doing is assigning your defensive resources to stop the things that never should happen from occurring, and then take whatever money you have left and apply it to that. And I think I mentioned earlier that many of these unacceptable outcomes stem from things that are sort of adjunct to what you're trying to accomplish with the mission. They're more security constraints of don't let people, if I'm trying to write a prescription, don't let that prescription be something that a bad guy can spoof. That way you can get illegal access to drugs just by submitting false prescriptions to a pharmacy. So the mission impact.
Hey, Scott,
yes.
Can I ask you just to pause for 1 second? We're going to try to reload the slides to see if we can make things a little bit better on your end there. So let's try to see if that help the situation on your end there.
Okay, I apologize. Was it just on my end, or was it everybody else?
I was seeing the slides, maybe a little bit fuzzy, but I never lost, I never lost the screen at all. So.
Okay. Well, so I will continue. Hopefully this will be a little bit better. And again, I apologize. It's just hard to keep track when I train of thought when the screen, something different pops up on my screen, and it would basically it would basically pop back up to the original slide at the beginning, which is kind of odd. So we've been using process modeling as a way to represent your cyber mission impacts. There's a bunch of reasons why process models are a good way to represent mission processes. And we first demonstrated that we could do this using commercial process modeling tools like iGraphics, but we found that there are reasons why that makes a very bad example of something we deliver. So we ended up having to roll our own so that we could tightly integrate this mission impact assessments with the rest of the cybersecurity game that I'll be describing to you. But these models are graphical, and you don't need technical expertise to see what's going on with the mission process. You can have submodels like you see here. You can use swim lanes to make what you're seeing, intuitively obvious of what the actors are or the components that are associated with the different actions that are there. It's an executable simulation, so you can run code when you perform these actions. The sort of secret sauce to the impact assessment tool that we developed is the ability to dynamically do control flows. So the arrow that was just highlighted is pointing to an activity that depends on a cyber asset, and you're basically able to say, hey, if I did this cyber asset, if I was doing this mission activity and this cyber asset was modified, this is the likely outcome that would happen. And that's essentially how this starts to work. And you can use it to compute the impact of any arbitrary incident. And here an incident is some cyber incident. I talked about the Dimfui effects occurs to one or more of the cyber assets. It starts at some particular time when you think it occurred, and you think it's going to last for some amount of time. And again, if you don't know those things, you just put bounds on them, and it will compute what best it can. And we actually can do things with this like run combinatorics, and I'll show you about what the combinatorics are and why they're useful. So what you're trying to do is you're trying to present a intuitively understandable description of the mission process. Here's the process itself. There's also a tree that sort of shows you how all the processes are interrelated with each other. And one of the other things that happens is you're done with a mission impact assessment model when you've essentially looked at all of the cyber assets that you have and done a mapping of all of the types of those Dimfui effects against it and map those to the outcomes that you want to avoid. It's quantitative, so it's going to actually take into account, it doesn't try and just normalize everything to 100. If something is 10,000 times more catastrophic than other things, that's kind of how you're going to score it. And by running combinatorics, it basically, you use the program to do things that other people are trying to compute with things like computing things like cut set analysis on a process diagram or things like that. By running the simulation combinatorically, you're going to get the choke points are going to show up because incidents, will always run through them. And if something happens, it's catastrophic. It's going to be weighted against things that are less catastrophic but happen throughout the mission process. And the result essentially is one of these mission dependency maps. These mission impact graphs, which shows you sort of criticality of, you've got IC assets on the bottom, you've got quantitative assessment for each one of the mission impact effects that can occur, and this tells you where the impacts will occur and what effects are causing them. So the next thing you want to do is to start saying, how do I go from impact to risk? So that's where we start bringing in the topological threat model, which runs against the cyber terrain model. And if you think about it, we're going to use that as a proxy for probability, or the likelihood that the attacks will succeed. And if you combine a consequence with the probability, you've got a risk score. And so that's how we go to risk. So we develop these computable models of your cyber terrain. They include things like trust boundaries, which represent places where you would supersede physical connectivity with logical connectivity, like firewall rules, those kind of things. We include basically hosts and applications and the data, and then implicitly there's data paths of where the data will flow through if it exists on two different places as part of your mission process. There's a place down in the middle where it says host pools, where you may not model a bunch of things that are cyber assets that are not really critical to the mission itself, but they become stepping stones. So you can just sort of say, I have 100 workstations here, and they may not be directly related to the mission outcome. but they're still there. And again, I'm afraid I just lost the screen again. The idea behind this model is it's meant to be computable. So what we provide is a attacker model which basically runs against that cyber terrain, and I'll sort of walk you through it here. It's a probabilistic model, so it works as a Markov process when you run it against a terrain model. And coming from the outside in, if you pick a particular asset, there's a probability that coming from the outside, you'll be able to attack the target. In this case, it's that Windows 7 host there. There are people who have access to that host, and if there's a huge population of those, the probability of them becoming compromised is whatever it is. Once you have gained access to that host, there's a probability that you can basically do whatever you want to some of the other, create effects to the other assets that are on that host, so that's having access. The way this works when you run it against the model is essentially you build up capability as you go. So having demonstrated that the attacker can compromise that Windows 7 host, if there's other Windows 7 hosts on that network, they are now at much higher risk if the network allows them to be physically connected, contacted from the subverted hosts. So there's a probability that you can use the same attack again on other hosts. There's a probability that you would have to use different attacks against hosts of a different type. And throughout, there's also the chances that you can steal credentials and they map as alternate ways to get from host to host without using exploits. So this is composable over multiple networks. So if I segment my network a number of times, this basically will continue to run until you get to the things that can cause impacts. And as simple as this attacker model is, it does capture the cybersecurity principles of least privilege, diversity, and segmentation. So there's a metric that was developed by the guys out of George Mason a number of years ago. It's called K0 day safety, which basically says your system is as safe as the number of 0 days that you need. This essentially is generalized that in a probabilistic Markov kind of form. So that there's a probability associated with how many 0 days it might take to get to the things that cause impact. And so this is probably the most important slide of this presentation. If you take all the things we've talked about, there's a system topology in the upper top left. There's mission impacts that you compute from your mission impact model. You can compute either direct impacts of I just attacked asset S1 or S2 or S3. You can also look at combinations of what happens if I attack S1 and S2 at the same time. Those, that may or may not have the same impacts. And all the way to, in this case, you have the worst case at the bottom, which is if I attack all of those assets, my impact is really high. It's 100 times bigger than my other impacts that are there. And I use the probabilities from the attacker model, and it produces this attack tree. On the left is I'm coming from the outside in. I can attack and compromise host S1. There's an impact associated with that produces an expected value. A little bit further to the right is I do S1, then I can go from S1 to S3 or S1 to S4. And those each have expected values all the way to the pathway on the far right that shows you, well, here's what it would take to compromise all of those assets. And yes, you have a high impact, but basically probability of being able to do all of them, given the way this network is configured, is pretty low. So it's actually fairly low risk compared to the other risks that are there. And just to sort of put things in perspective, it looks really simple when you see a simple listing of attack this node, then this node, then this node, when you see it in this form. But behind the scenes, keep in mind that in cyber systems, security rules are sometimes not bidirectional. So sometimes there are certain ways that you have to do things in a particular order. So what you're seeing here is the best order that the algorithm found for attacking this set of hosts. And so it's a little bit more complicated than just saying all these hosts added together. And so, apologize. So this essentially produces a risk metric where that risk metric is either the sum of all these expected values or the worst case. And that, when you run it against your initial model, becomes the baseline. of, well, this is where I think my system does. And if you have two different versions of the same system, if you got them scored in terms of the same impacts and valued those impacts the same, and there are different topologies associated with how they're composed, in theory, you can make system A, simple implementation A versus simple implementation B, look at those risk scores and see which one might be better from a security and resilience perspective. But what we're going to be doing next is taking that resilience score that's on the baseline and adding, security and tools to reduce those risks. And so here's an example of the fact that all I'm really trying to highlight with this slide is that there's a bunch of cybersecurity techniques that are listed here, and each one tends to be good for some things that are and not so good for others. So if your issue is interception, diverse redundancy isn't really the thing you think about as the way to solve interception problems. You think about encrypting things, you think about reducing privileges, or you think about non-persistence. And so there is this natural mapping of once you know what the threat is to the assets, well, you kind of get an idea of which security tools are the ones you should be applying. So that's really all it's supposed to do. So here's a concrete example of a system we did an assessment of, and what you have here is a bunch of cyber-defended methods that were proposed. In fact, this was done for a point-of-sale system being used in the commercial sector, and what the people up at the National Cybersecurity Center of Excellence were doing was developing these reference architectures to help encourage people to do best practices. The trouble with the reference architecture is that it's not necessarily a one-size-fits-all, and in developing the reference architecture, the guys up there get given free stuff by vendors. So if you take all the tools that they put together, they have a very, very expensive solution that costs like over $250,000 if you were to try and buy all the things that are in the reference architecture. And small companies just maybe can't afford to do that. So you can use what we're doing with the cybersecurity game to sort of figure out, well, if I could only afford to spend this amount of money, these are the ones I'd use. And so these are all things that mostly people would recognize, things like non-persistence, things like whitelisting. There's a couple things that are specific, like text session tokenization was specific to this domain. But these are all basically tools. You also consider things like segmenting the network. And we have to model those. And so what we've done is model them in the following way. There are things that reduce the chances of attacks succeeding. So here, encryption is really good for stopping interception, but it's absolutely no good at all for stopping interruption attacks. Things like server hardening is kind of not really good at anything, but it's sort of somewhat useful for everything. You can look at the process. If you had a single server here, if that becomes a point of failure, well, if I add a backup server, now I have two pathways. They joined in an OR, and now the attacker has to essentially basically compromise both of those servers to break that process path. You can also do things in process space, like consider different timescales of recovery. So you may have the choice of, do I recover, pay for a really expensive recovery solution that's based on virtualization containers, or do I do something where I just, or do I need to, all I have to do is recover that post off of a backup tape. It really depends on what the temporal constraints of that process are in terms of creating impacts, but you can essentially model those and put them into the solution, and it will trade them off of, well, in this case, you don't need to use the expensive solution for that. And then also, there's the problem of being able to do things like change firewall rules or change the network itself. You can add diversity to things by changing the types of things. And so all of the things that are listed in that previous list manifest themselves as one or more of these, so that when we start applying them, we start building this game tree where we apply one of those techniques. We then let the attacker model run on that and say, well, how has this changed my risk score? And so each step as you go through this game tree represents being a point in this Pareto chart. And what you're looking for is these lines at the bottom, which are essentially the Pareto optimal solutions given any particular amount of money you're going to spend. And that's essentially what you're doing, is you're using the tool to do things like to do composition of the security methods you have. The Complication, of course, is that not all of these tools compose independently of each other. We don't assume that they do, but if they don't compose independently of each other, it's up to, you have to take into account in your model that these things would combine in a non-additive type of way. And a simple example of that would be something like if you were to apply a host-based intrusion detection system, combine that with a network-based intrusion detection, chances are, if the host-based intrusion detection you think solves 40% of the problem, and the network-based intrusion detection you think solves 30% of the problem, how much of that 30% is an overlap with what the host-based system does? And so you have to have a lot of knowledge to be able to apply this stuff, which is why we think it's important to have experts be able to provide these models as opposed to leave it to end users to have to guess this for themselves. So the result is this portfolio analysis, and this is essentially what we try and provide the decision maker, which sort of shows you what the different compositions are, and it shows you what, how they compute and combine with each other. So you get that Pareto curve on the bottom, and you can see exactly where there are combinations that just, spend a lot of money but don't do a lot to reduce your risks. So this is what we're producing. And typically what we've been finding is that you get these situations where if you look at the knee of this curve, you essentially do your first pass and cover all your major risks, and then at some point you start using other tools to look at the highest remaining risk, but you're doubling up on things you've done, so your return on investment becomes lower. And it helps take things like the reference architectures that were being developed at the NCCOE and be able to say, well, if you're a small office, maybe these are the tools that you would want to be investing in if you only could afford to spend $50,000 instead of the $250,000 for the full reference architecture. So, in a nutshell, that is the complete sort of walkthrough of the cybersecurity game. I wanted to give you a little bit of a comparison to some other work that's out there. There is a resilience analysis methodology that is that has been developed by other folks, and in basically the cyber resilience engineering framework, CREF, and some other work that my colleagues at MITRE have done. And what they suggest is the set of steps that are on the left under cyber resilience analysis. What do we care about? How do the cyber threats affect the missions? What do we build on? How do we improve mission assurance? And then what do we recommend? And if you take the set of things that I just described, the resilience context is telling you what you care about and figuring out and combining that with the unacceptable outcomes and how you're going to use the metrics is going to tell you, what you're going to measure. The incident impacts, whether you're trying to do, make it resilient in terms of availability or confidentiality or integrity or even, being able to spoof signals, those are the things that you either do some of them or all of, or just a few of them. We are using attack trees to, I just lost the screen again, apologies. There we go. We're using attack trees to compute the likelihoods. We compute a risk baseline. And then you basically are doing, composition using algorithms to figure out what's the best way to mitigate those risks. And what's important is when you're done, we've built these models, and those models will leave behind. So if you want to update it later, some new threat has changed, some new security tools out there, you can basically just change the models and rerun the program, and you'll get new assessments. So to summarize, it's trying to codify in software a lot of the things that cybersecurity risk assessors are doing manually and in their head. It's meant to be, you focus your time on describing your system, understand, what your mission process is and how incidents will impact those outcomes. Describe your cyber terrain, and you just explicitly link the architecture to the mission in the program, and then you run the program. Let the program do all the work. Those models are the formal artifacts that characterize your assessment behind, so that somebody can do it again. You can do this for as-is systems. You can do it for as-might-be systems. The claim is that this is comprehensive and consistent because essentially you're leaving it up to a program to do all the work, and you're just providing the models it needs. I mean, if you get the models wrong, it's going to give you not very good answers. But if you get the models right, then you should feel good that it's comprehensively assessed those. And it's focusing on quantitative assessment. So there was a paper that somebody wrote that said, the next thing I want to do is figure out important questions like how much diversity is enough. Well, given that this runs as an attacker-defender game, and you've defined the space in the models of what the terrain is, what the mission outcomes are, and what the attack space is, it actually can help you determine how much diversity is enough. If you keep adding diversity to your defenses, as long as that is reducing the risks so that some other component isn't the best target for the attacker, it's a useful thing. But at the point where you've added enough diversity to the components that you have in your system, and it doesn't change the fact that this other component is now the best target that's out there, then that's the time you start looking at the component and figuring out how you should be defending it. So it's meant to be, it can answer sort of holistic questions like that. Talk a little bit about some ongoing and future work. The attack model I described here is very simple. It's meant to be very simple because it's meant to sort of encourage architectural design principles, like I mentioned, least privileges, diversity, and segmentation. But we look at adding things like the minor attack framework and things like time to compromise models. One of the biggest issues that I kind of glossed over in there is the fact that we are relying very heavily on expert subjective assessment on how well cybersecurity methods work and how they combine. So we did an assessment where we're looking at multi-factor authentication applied to a system, and getting any hard data on how much multi-factor authentication reduces the chances of access is almost impossible because the results are just not there. It turns out that in some of the community, for example, like the biometric community, they can give you numbers about performance metrics and ROC curves on how a retina scan or a fingerprint scan will has true positives and false alarms. But things like, your secure ID, you kind of just assume that it works, and there's no real hard data on that. So we need to be able to do that a lot better because right now we rely very highly on subjective assessments. One of the ways you get around the fact that we have all this uncertainty is to use basically parametric distributions on things. The cyber mission impact assessment model very happily will do all of its impact assessments if you assign distributions to things. Most popular distributions are things like a triangle or a beta-pert distribution with a min, a mode, and a max. So you say, I think the answer is this, but it's definitely greater than this and less than something else. And now you're pulling all those numbers out of the distribution, and what you get when you run the models is this nice, really hairy joint distribution that would be very difficult to compute by itself. I apologize, I lost the screen again. There we go. There are aspects of the way the game works that are highly parallel. I call them embarrassingly parallel. So we've done a little bit of work looking at putting Kubernetes to a high-performance cluster, so you can do all this stochastic modeling, and it works very well. And then the other thing I would say is I kind of feel less than satisfied that we've kind of had to develop this as a off-to-a-side, standalone, yet another tool that you would apply. What would really be better, this has been described in this context and sort of as a way to do model-based cybersecurity engineering. It would be much better if you could just get these methods incorporated into the model-based security and model-based engineering tools. Because essentially the cybersecurity engineering isn't meant to be off to its side. It's meant to be associated with all the other mission engineering that you're doing. So you want to be able to measure to leverage all the other artifacts that people are producing anyway and perform that analysis in conjunction with other assessments. And so that's kind of what we want to be able to do. Off the screen. screen. So I think at this point, I think I am done. That's a summary of the cybersecurity game. I would welcome anybody to provide, feel free to ask any questions that you may have.
Okay, thank you, Scott. That was that's interesting presentation, interesting work you've got going on there. So one of the questions kind of popped into my mind as you were doing the presentation. You've got your cybersecurity game, and of course there's the the requirement to do the risk management framework process, and in order to get the assessment and authorization for systems to be blessed to operate. How does the cybersecurity game, how would you say that relates to the RMF process? Could that help the process, complement it? Your thoughts on that?
Yeah, so it's interesting. There was a meeting yesterday which was talking about exactly that same issue, and the answer really is that RMF, as it stands, is more qualitative in terms of its analysis and less quantitative. I would claim that everything that the cybersecurity game is doing are the things that you want to be doing when you do an RMF analysis, but they're not prescribed in RMF, so there's no reason why you have to use, quantitatively assess your impacts as opposed to just put them on a simple, risk grid and say, low, medium, high types of things. So I really kind of use the cybersecurity game as what I would hope to be as sort of the RMF next. And the evil, clever idea I have is that part of the problem with RMF is you do all this analysis. It's not necessarily prescriptive. So, for example, there's nothing in RMF that supports all the portfolio analysis that we have programs to do here for combining things into a security portfolio. And then you have to produce all these documents that show your assessments, and then you can use those documents to get your authority to operate. So for small companies, it's a very high amount of effort to do all those things. And what I think you could do with something like the cybersecurity game is you're focusing on building the models. You let the programs do the analysis. All you need to do is keep the models up to date and maybe download the latest threat models to see how it changes, how the latest threats will map to your architecture. And I think you could write programs that could use the model-based artifacts to produce all of the compliance types of documents you would need. And I think that would be a huge thing to basically be able to support the kind of things you want to do in RMF, but you let the computers do all the hard work that's behind the scenes, and so it makes the cost of doing those things much lower and make it more likely for people to do it and do it well.
Okay, so then to follow up on that, so then how much effort does it take to develop the models in your system?
Yeah, so that's always an important question to ask about any of this stuff. One of the problems that we've been running into is we've been asked to assess systems that already exist, and what we find is that the systems that already exist are not adequately documented, so you spend most of your time just trying to back solve what the system is doing. Here's what it was designed for. Here's how they were measured. Here's how we're going to measure that for better, same, or worse. So you spend most of your time just doing the understanding the system. If you're doing this as we hope to, we present here, which is you're doing this at design time. You've created these artifacts so that they're there and you can continue to use them. But so typically, I would say it takes you anywhere from a couple people, a couple months to go through a system and just understand it well enough to start building the models. Building a CMIA process model is, you can actually build the models really cheap, really quickly. I mean, the way the process modeling software works, you can go from nothing to a fully executable model in a couple days. But then you should spend a long time validating that the results of that model is doing what you expect, and you work with subject matter experts to make sure that model is producing outputs that are consistent with what you expect. The terrain models, we're building those manually right now. That's certainly not the way to do it. We have other work that we've been doing on automated mission dependency mapping, where there are commercial products now that can build you network maps, and we can look at other mission relationships by looking at things like net flows or user access logs and those kind of things. And so we're trying to semi-automate some of the building. But right now it's a little bit, I would say anywhere from, typical 3 months to do this kind of assessment, starting from scratch on a system. And then further iterations are much cheaper because you have all this information to build on.
Oh, okay. So, and what kind of expertise do you think is required for somebody able to do this? How what would they be required to know? Where do they pull the information from? What's your thoughts on that?
Could you say that again, please?
So the expertise level needed to actually develop the models, and then also I had a question about where are they getting the information from to develop the models? What do they need to develop those models?
Right. Okay. So one of the things that's difficult about cyber risk assessment is if you go into things like CVE and CAPEC, is you realize you need to know an awful lot about cybersecurity and the way computers behave and operate, to understand what the risks are. And so we think that that's a big ask for people in small companies to be able to have access to that expertise. So we would recommend that people can use the attacker-defender models that we create that capture expert-level types of expertise as something that they can just use. And if they if they know more than we do, they can change our models and change the values and go through with that. As far as building the models itself, you do need to understand your mission process. That's always going to be dependent on the organization. So that's you need somebody who understands how to build models, who understands the mission process to be able to build the impact models. I showed you the impact models here as a process diagram. I think that really has got a lot of advantages to doing it that way. But at its simplest, if you really just said, here's all my cyber emission impact, here's my cyber assets, and here's all the dim FUI effects against them, and here's the mission outcomes that my mission people told me I didn't want to happen, and how these effects map to one or more of those impacts, you can use that as an impact model. So that's a combination basically of understanding and enumerating cyber assets and understanding the mission needs, and then building the cyber terrain model is, like I say, it's kind of droll, and you just need somebody who understands enough about your network. And trust me, when we've pretty much every time we've looked at a real network, they give us a network diagram, and it's certainly not reflective of what the network is doing right now.
Okay. Thanks for the feedback on that. So, one of the questions, a couple folks are that are online. They're interested in is the software, the tool that you've developed, is that available for other folks to access and use? What's the status of this software, the cybersecurity game that you've developed?
My understanding is that because we are at FFRDC, if a government person wants access to it, they should be able to ask us, and we should be able to get it to them. Been looking into the idea of public releasing the application itself. Keep in mind that truth in advertising, the system does all the things that I've described and claim it does here, but what you've got is essentially a prototype that probably doesn't make the model building as easy as it needs to be. It makes some of the debugging of the models harder. But once you've built the models and debugged them, the thing will run happily and do all the combinatorics. So we're looking for the idea of maybe making this available. Haven't got any approval on that yet, but my understanding is if you are a government organization, you should be able to ask for it, and we should be able to give it to you.
Okay, great. Well, that gives us a way to follow up and to pursue that, explore that avenue. So we've kind of hit the our time for today. But there are, I think there are a number of other questions that have come in online. I don't know if you're open to it, but if we gather those questions up, we have tech forums on our CSIAC website. If you, like I said, if you'd be willing, we can share those additional questions we've received with you, and maybe you'd be up to providing some answers that we could post online for our attendees. And I do want to thank you for taking the time for spending with us today and sharing your expertise. Like I said, I think this is a interesting work and valuable work, and we're appreciate your activities in this arena.
Well, thank you for the opportunity to present. I just want to touch on one little thing. I mean, there was questions about how do you use this if you're a small company, if MITRE doesn't make it available. So keep in mind, MITRE is an FFRDC. Our job is to solve our customers' problems, which are government, and produce research that produces prototypes. I actually gave this presentation at last year's model-based summit. That's something that NIST hosts every year, with the particular idea that hopefully there are nuggets in here that the model-based systems engineering tool developers can start to integrate into their tools. So hopefully you'll start to see some of this stuff that's there. And the thing is, because MITRE is an FFRDC, we don't develop and we don't sell products. So there is work with our technology transition office that has me talking to various people who might want to commercialize this. But as a MITRE person, all I can do is say we can give it to the government, and I'm looking to see if I can make the application available to pretty much anybody, because we don't sell it, we don't sell things.
Okay, well that's good to know too, because there may be some other folks on the line that would be interested in trying to take that and develop it and turning it into a product that other folks could utilize. So yeah, that's good to know. Clarifies the the situation with the organization you're in. So
and so if there are people who would like this, if they want, feel free to send me a contact, and I can add you to the list, which basically goes to help bolster the argument about why it's worth even taking our prototype as is and making it available to people, because I think it's meant to be. It's not meant to be a piece of research that just does nothing. It's meant to be a tool that people can actually practically apply.
Okay, that sounds great. Well, you heard Scott. You can, if you are interested, you can send a message to him directly, or if you want to send it to us here at CSIAC.org, we can get that info to him that way as well. And take if you're interested, take Scott up on his offer, and we'll try and move this forward. So once again, Scott, I thank you for your time and the information, and we'll just wrap up for today, and hope everyone has a good day, and we'll hopefully see you in the future. Thanks. Bye-bye.
Everybody.